Namaste to one and all. Today we are going to discuss a small topic that is known as quantum numbers. It's there in atomic structure. Right. So what are these quantum numbers? These are the numbers. By knowing about these, we can say what is the position of electron in an atom. Actually, as electron is a very smaller particle, we can't say actually what is the position of that. We can't say actually what is the position of that before knowing this quantum numbers, because as it is a very smaller one, if you are able to say the position, we can't say what is the velocity of electron, and if you are able to say the velocity of the electron, we can't say the position of the electron, right? So to say almost the position of the electron, here we have these numbers, quantum numbers, which are going to say us what is the position of electron inside an atom. So here these quantum numbers are of four types. What are those? First one is principal quantum number. Principal quantum number. And second one we have here, that is known as azimuthal quantum number. Azimuthal quantum number. And third one we have here, that is known as magnetic quantum number. Magnetic quantum number. So before going to these quantum numbers, just I'll compare this atom as a school. Compare the atom as a school. So here if you take the school, inside the school we have some class. Inside the class we have some sections. Inside that section we have some benches. In each bench some number of students are sitting. So if you take this as an atom, that is a school, we are taking it as an atom, and class we are taking as a shell. The class whatever is there here, this we are taking as a shell, and each shell will have some subshells. So whatever the sections are there, this I am taking it as a subshells. In each section some benches are there. So these all I am taking it as orbitals. Orbitals are nothing but benches in one class. So try to understand the concept here. The atom, that is nothing but the school in which you are studying, and in that school we have some class. This class only we are saying in the form of a shell, and in that shell many number of subshells are there, that is nothing but sections, and in each subshell we have, that is in each section we have some benches, that each bench we are going to say that as an orbital. Now actually we have one more quantum number also, but after completing these all we'll go to that because it's a very easy one. So first coming to the principal quantum number. When you know about principal quantum number, what you can say? What you can say about the position of electron? We can say in which shell the electron is present. That means actually we are going to give a symbol for this principal quantum number, n, right? So this n can have the value 1, means electron is present in first shell, maybe 2, electron is present in second shell, or 3, 4, 5, like this whole numbers we are going to give. When you know the principal quantum number value, we can say what is the shell in which electron is present. Based on that we have the formulas. We can say what is the energy of the electron. We can say what is the radius of the shell in which that electron is present. Means the distance from the nucleus to the electron. We can say what is the distance, right? So these are the values. Like in one school, in which class you are there, we can find out with the help of the principal quantum number. Next coming to azimuthal quantum number. Azimuthal quantum number, we are going to give one symbol for this. What is that? L, right? So this L will have the values starting from 0 onwards up to n minus 1. Means in one class how many sections are there, it depends on in which class you are present. Maybe for example in first class you are there, it may be 2 sections. Second class if you come, it may be 3 sections, like that, depending on the strength of the students, how we are making into sections, like that. Here also the number of sections, number of the subshells will depend on which shell the subshells are present. Like here if you take azimuthal quantum number value, it starts from 0, it will be up to n minus 1. Means if you take the first shell, if you take the first shell, what is the value of this azimuthal quantum number? Only 0. Means only one value is present, that is 0. If you are taking the second shell, two values are possible. What are those? 0 and also 1. If you take third shell, the values will start from 0, 1 and also 2. So, 3 subshells are present in third shell, 2 subshells are present in second shell, 1 subshell is present in first shell. Like that, shell number is equal to number of the subshells. The value of this azimuthal quantum number starts from 0. Value is 0. How many values are there? 1. Here values are 0 and 1. How many are there altogether? 2. Here values are 0, 1 and 2. How many values are there together? 3. Like that, in each shell, how many subshells are there? That number of subshells is equal to number of the shell. Next, coming to magnetic quantum number. Magnetic quantum number, we are going to give a symbol for this, that is nothing but M. So, the value of this M, magnetic quantum number, will start from minus L. It will start from minus L and it proceeds up to 0 and it will end with plus L. That means, if you are having one subshell whose value is 0, subshell value is 0, then we have only one magnetic quantum number, that is 0. If you are having 1 as a subshell number, means azimuthal quantum number value for that particular subshell is 1, then the values will be minus 1, 0 and plus 1. If you go to the subshell which has a value of azimuthal quantum number as 2, then you will have minus 2, minus 1, 0, plus 1, plus 2. Totally 5 values. Like that, here these are the values present. Just once again we will compare the atom with the school. Total atom is present here like a school. In that, many number of shells are there. Like you have classes in one school, and like that, sections are there in each class. Subshells are there in each shell. Number of benches are present in each section. Like that, many number of orbitals are present in each section. How many number of benches are there? Like that, we have many number of orbitals present in one subshell. Now, here we'll see some of the different terminology here, what we are going to use. For subshells also we are going to give some names. For orbitals are nothing but from magnetic quantum number, whatever the values are there, for that also we are going to give some names. The names also we'll see, and one more quantum number we'll see. Right. Now we'll see the next fourth quantum number, spin quantum number. This spin quantum number will give us the idea how this electron is rotating around itself. Actually, electron in an atom revolves around the nucleus, and also along with that it rotates around its own axis. So whether it is rotating around its own axis in clockwise manner or anti-clockwise manner, we can know from the spin quantum number. Here we are going to give a symbol for this spin quantum number, S. This S will have only two values, either plus half or minus half. If the electron is rotating in clockwise manner, up arrow will write as a symbol, or plus half. And minus half is the value we are going to give for this spin quantum number when electron is rotating in anti-clockwise manner. So in one orbital, 2 electrons will fit. In that, one electron rotates around its own axis in clockwise manner. Another electron rotates around its own axis in anti-clockwise manner. Right. So here, with some examples we'll see, and also along with that some more formulas are also there. Now here, you want to say how many subshells are present in one shell. So number of subshells in a shell. How to write this number of subshells in a shell? So already we have seen that in the first shell we have one subshell, second shell we have two subshells, third shell we have three subshells, like that. So number of subshells in a shell means that is equal to nothing but n. What is n here? Principal quantum number. How many number of subshells are there? How you will understand? When you know the principal quantum number, you can say what is the total number of subshells in that particular shell. Same like that, you wanted to say number of orbitals in a shell. How many number of orbitals are present in that particular shell? Right. Now with one example we'll see. First shell we have here, n value is 1. In that L values we have here totally how many values will be there in the first shell? Only one value, 0 to n minus 1 value, no? So 0 value is there. In that how many number of orbitals are there? M values we have here, only one value is there, that means only one orbital is present. So here in first shell we have one orbital, right? Now we'll come to second shell. Here we have L values totally 2, 0 and also 1. In 0 we have only one orbital, that is having the magnetic quantum number 0, and here in the first subshell means azimuthal quantum number 1 is there for the next subshell. That subshell will contain 3 values for this magnetic quantum number, -1, 0 and +1. Altogether how many we have here? 4. Second shell contains 4 subshells, 4 orbitals. 2 subshells and 4 orbitals. Third shell we'll see here 0, 1 and 2. 0, 1 and 2. So in 0 we have only 0, that is magnetic quantum number value only 0, 1 value is there. And coming to this one we have here totally 3 values, -1, 0 and +1. And in this one we have totally how many values we'll get here? -2, -1, 0, +1 and also +2. Totally values are 5. 5 plus 3, 8 plus 1, 9. So third shell contains 9 orbitals. Second shell contains 4 orbitals. First shell contains 1 orbital. That means we can say simply n square is the formula for number of orbitals in that particular shell. Same like that, you wanted to say how many number of electrons are present in one shell. In one shell, how many number of electrons are present? Maximum number of electrons. Maximum number of electrons accommodated in a shell. How many number will be accommodated? Now you see here, in one orbital, you should remember like in one bench, 2 students will sit. In exam time, how you will sit? Only 2 members. Like that, here also, in one orbital, maximum number of electrons accommodated are 2. Right? So, like that, here, as we have in first shell, only one orbital is there. 2 electrons will fit. Second shell, we have altogether 4 orbitals. So, 8 electrons will fit. Third shell, we have total together 9 orbitals. So, how many electrons will be there? 18 electrons. So, simply we can write here 2n square is the formula for maximum number of electrons accommodated in one shell. Maximum number of electrons accommodated in a shell, we have the formula 2n square. Right? Now, here we'll see number of orbitals in a subshell. Already about shell we have seen. So, coming to subshell. In one subshell, how many number of orbitals are present? Right? Now, before going to this, first of all, we should know what is the subshell and all. Means some names are given here for the subshell. So, that we'll see. Based on that, we'll see the remaining things. So, here we have subshells. Based on the azimuthal quantum number value, whatever we are writing, we are giving some name for that based on its shape. If the subshell is present in spherical shape, we write S. If it is present in dumbbell shape, we'll write P. If it is there in double dumbbell, we'll write D. If it is there in complex form, we'll write F. Means here, azimuthal quantum number value for this first subshell, S subshell is 0. For P subshell 1 and D subshell 2 and F subshell 3. These are the values we are going to write for these subshells. Right? Now, here you see, in S subshell, how many number of orbitals will be there? Only 1. Magnetic quantum number value 0. In P subshell, how many number of orbitals will be there? 3. -1, 0 and +1. So, here I will write number of orbitals, 1 here, 3 here. Now, here in D subshell, how many number of orbitals are there? -2, -1, 0, +1, +2. Totally 5 we have. 5 are there here. Now, here we will come to F subshell. -3, -2, -1, 0, +1, +2, +3. Altogether we have here 5 plus 2. Totally we have here 7 orbitals. Now you see, just simply you see here 2 into 0 +1, 2 into 1 +1, 2 into 2 +1, 2 into 3 +1. Like that we have this number of orbitals present in a subshell So we can write simply the formula 2l plus 1. This is the number of orbitals present in a subshell. Same like that, we can write maximum number of electrons. Maximum number of electrons accommodated in a subshell. Maximum number of electrons accommodated in a subshell. Easily we can write based on the before formula. Because here we are getting the number of orbitals 2l plus 1. So what is the number of electrons present in each orbital? In one bench, how many students will say? 2. So in one orbital, 2 electrons will be accommodated, one rotating in clockwise manner and the other one rotating in anti-clockwise manner. So what is the formula we are going to write? 2 into 2l plus 1. Otherwise simply we will write 4l plus 2. 2 into 2l plus 1 is nothing but 4l plus 2. So these are some of the formulas. These are some of the formulas. Based on this, we can write easily. Means whenever we are getting electrons here, we have to say the formula is, it is not number of electrons actually, maximum number of electrons. Maximum number of electrons accommodated in a shell. Maximum number of electrons accommodated in a subshell. Anyway, maximum number of electrons accommodated in orbital, we know already, that is 2. Right? So spin quantum number value, only 2 values are there, plus half and minus half. N values start from 1 onwards, it will proceed like that. And L values will start from 0 onwards up to N minus 1. And M values based on L value. Based on L value they are there. So only plus half and minus half. Right? So these are the quantum numbers. Based on this only we can say what is the position of the electron. If you like the video, please comment in the comment box and also click the like button and subscribe my channel if you have not subscribed before. Thank you.